How's everyone doing? Sorry about that. Totally lost track of time. It's like, whoa, it's already 1 o'clock. How are y'all doing? Can you hear me? Yeah.
Yep.
Good. Hope you had a good break. And hope you've been enjoying the take-home midterm. Hope it's been going okay. Caden, what happened to your hair? It's all gone.
I cut it.
Yeah, I see that. Never a bad time for change. All right, well, we need to get down to business, I guess. Any questions before we get going here? No questions on the take home? Oh. All right. Okay, so in terms of where we are, we have finished up, we've got partial derivatives taken care of, tangent planes we've got taken care of. Chain rule, we're not quite done. We're going to just finish up chain rule today, and then we will get into the directional derivative and the gradient vector. Okay, so we're a little behind because these dates were off. It looks like we're about a day behind, but it looks like we might be catching up. But I already know that Lagrange multipliers, this section usually takes 2 days. This is a really tough section right here. So yeah, let's get down to business. So I know it's been a while. And the last thing we were doing was the chain rule, right? So we were talking about how do you take the derivative of functions of several variables. And we had this idea of like this tree diagram. I know this is sideways, but we had this idea of this tree where you can go down the branches of the tree and talk about what straight derivatives are possible or what partial derivatives are possible. And that's kind of where we were. We were at the end of that, but we didn't quite get through everything. So let me see, where is it? There it is. So we had gone through these examples, we had ended here, and now we get to what we call the general case. All right, so this is kind of like wrapping everything up into one final thing here. So it says here, and this is going to seem weird when we first do this. We're trying to discuss implicit differentiation, but with functions of more than one variable. So we know what implicit differentiation looks like in Cal 1, but what does implicit differentiation look like here? So it says, suppose we start with a function of x and y, and that means you can solve the function, or you can solve the equation for z. Then if we take this equation and we move the function of x and y to the left-hand side, so subtract it on the left-hand side, we get a new equation that's equal to 0. And what we do is we define capital F of x, y, z to be the left side of this equation. So if you look at, we're going to do an example, but when you see the left-hand side, this expression is going to have x and y in it. This expression has z. And so you can look at the entire left side as some new function of x, y, and z. All right. And now we have to, I guess, be clear that x and y may depend on one another. And actually z, we know depends on x and y, but x and y themselves might depend on one another. So we need to differentiate using implicit differentiation. And here's how it works. So there's actually a formula. This is what's nice about implicit differentiation, is that there's a nice formula for it. We don't actually have to go through all of the work for it. We can do it for each problem. We can actually do the mechanical work of implicit differentiation. But at the end of the day, they're all going to turn out to have this final form. So here's, if we want to know the partial of z with respect to x, this is the formula for it. And I'll copy this and bring it to the example we're going to do. And if we want to know the partial of z with respect to y, here's the formula for it. All right. And there's really only 2 differences between the formula. Here, I put it in red here, partial with respect to x here of this one. And on the other formula is partial with respect to y. So let's do an example. So I'm going to grab this, go take this over here, and start today's notes. All right, so here we go. So notice what we have here is an equation, right? This is an equation that involves x, y, and z. And so we do not have, at this point, we do not have z is equal to some function of x and y, right? We don't have that. Now we could try and solve this equation for z, but do you all see how that would be problematic? If we tried to get z by itself, these two terms would have a z in it, but then you couldn't really factor a z out without leaving a z in this term. So it would be very difficult to get z by itself. But we still are interested in two things. We want to know what's the partial of z with respect to x, and we also want to know what is the partial of z with respect to y. Those are the two things we want. And because this is a surface, right? This is some sort of surface. It has three variables related to one another. So it's some surface. So we're trying to say, okay, if we stand on the surface at some point and we point in some direction, then what is the slope of that tangent line there? And if we point the other direction, what's the slope of the tangent line? Do y'all know what I mean by direction? Like parallel to the XZ plane or parallel to the YZ plane? Those were the two directions. Do I need to bring up the picture again, or do y'all remember that? Let me bring up the picture. Only because we're going to do 11.6 today, and it's going to be different than what I'm saying right now, and I don't want there to be any confusion. So let's see. This was 11.4, I believe. No, 11.3. Sorry. Yeah, partial derivatives. So we had this idea that when we were on a surface, we could either have a plane cut through a plane that's parallel to the XZ plane, and then look at the slope of that line, or we could cut it the other way with a plane that is parallel to the YZ plane and look at the slope of the tangent line there, right? One of those is the partial with respect to X. The other one is partial with respect to Y. So we want to do the same thing. That's what we're trying to do. We're trying to achieve the same thing of finding the slope of those tangent lines, but we're trying to find it when this is not given to us explicitly as a function of X and Y. All right, so here we go. Going back to the notes, it says that if you know that z is a function of x and y, we rewrite the equation so that we get basically everything on one side equal to 0, all right? And then we apply this formula and this formula, right? And now the left side, though, remember the whole left side is our capital F function. So what I'm going to do here is I'm going to take this equation. I'm going to just bring everything to one side, which practically is already there. I just need to bring the 1 over. And now all of this over here is our capital F of X, Y, Z, right? We are defining that to be that. Now, according to the formula, I'm going to bring the formula back up here. Let's start with this one. If we want the partial of Z with respect to X, partial of Z with respect to X, we need to take the partial of F with respect to X and divide it by the partial of F with respect to Z. So those are two different things we have to do here. So let's start with trying to determine what is the partial of capital F with respect to X. Now, what does that mean with respect to X?
We hold everything else to be a constant, and X is the only thing we take our derivative to be respect of. In respect
okay, so
to.
X is the only thing that we are going to treat as our variable, right? And so what about Y? We treat Y like it's a what?
Like a constant.
Like a constant, okay. And what about Z?
Also like a constant.
Okay, let's try it. Let's see what happens. Okay, so when we take the derivative of this here is what? We're just going to do term by term, right? So the derivative of x cubed with respect to x would just be 3x squared, right?
3x
Okay, and now we take derivative of y cubed, but we're treating y like a constant. So what do we get here?
just goes away.
Okay, so it's just 0. So I'll say plus 0. Plus, okay, next one.
So z would also be 0 if you're treating it like a constant.
Okay, what do y'all think?
I think it's also 0.
Okay. Let's see here. 0, treat that like a constant. What about the next one? So what would we have to do here?
So it
Oh,
is
we
0, x, y, z.
You're treating your y and your z like a constant, and the 6 is a constant, so the only variable there is x, and derivative of x would be 1, right? And everything else just comes along for the ride, so you get what, 6 yz. And then here, derivative of -1 is 0, right? And that's it. So I'll put plus 0. So at the end of the day, we get 3x squared plus 6yz, and that's it. That's the partial of f with respect to x. Now we do the same thing, but we do the partial of f with respect to z. Partial of f with respect to z. You want to follow the same ideas? We treat the other two variables like constants, and we see what happens with z, or with the function f as z is our variable and x and y are held. So derivative of x cubed would be 0, derivative of y cubed would be 0, derivative of z cubed would be 3z squared. And then plus, what about here? Derivative of this with respect to z would be
6xy.
xy. And then derivative of -1 would be 0. Okay, so now we're ready for our answer. The partial of z with respect to x should be equal to, let's see, the negative, right? We need a negative because there's a negative in that formula. And then it's going to be this one, 3x squared plus 6yz over, now the bottom, which is just 3z squared plus 6xy. Now, I want us to understand what we're saying here, all right? Because this is where things get a little bit lost. We're saying that this right here is a surface, right? But it may not necessarily be a function of x and y in the sense that it wouldn't pass that vertical line test. Like if we punch a hole through the surface, it may hit the surface in more than one place, kind of like a sphere, right? Take a sphere and we punch it. We might punch it here, here, and then come through it and then pop out the bottom like that. So even though a sphere is a surface, the equation of a sphere would look something like this, where we couldn't get z isolated. What this is saying is that if we somehow can look at this as a function of x and y, if we're able to go to this point, we should be able to find the slope of the tangent line there holding y constant. That means cutting through with the plane. And here's what it should be. Now notice in this derivative, in the slope of the tangent line here, we need the x, the y, and the z coordinate of the point. You need all three values. And that would, see, that's how you distinguish yourself from being at that top point or bottom point. Once you give me the x, y, z, I'm either at this one or this one, right? That's why our answer contains all three variables in it. All right, does that kind of make sense? Kind of makes sense. Now, let me show you something. I want to show you why this formula is useful to us. Because if I go back up to here, useful, and when I say useful, I mean a shortcut, okay? What do we want to know? We want to know what the partial of z with respect to x is, right? That's what we wanted to know. So if I just take that equation up there and I just take the partial with respect to x on the equation, you know what, let me go to the, it doesn't matter, I'll do it on this one. Okay. Now, we did not do this, right? We did not do what I'm doing right here. What we did is we said, we're going to call the whole left side capital F, and then we're going to do these two derivatives, and then we're just going to put them into this answer. That's what we said we were going to do, right? And you accepted that on faith. I'm showing you now that had we gone through like the slower, longer process, we would get the same answer, but you wouldn't want to do it. Let me show you. Let's see how it works. Let's take the partial with respect to x of everything. So this first one would be 3x squared, right? Plus, now this is where things get weird, because the what is the partial with respect to x of this, right? Well, we treat that like a constant, don't we? Because we're doing the partial with respect to x. That means you hold y constant. So that should be 0. Here's where things get different, because the partial of z, the partial of z cubed with respect to x is not 0 if we are treating z as a function of x and y. So what would happen on this step is you would get 3z squared times partial z with respect to x. That's chain rule, right? 3 comes down, subtract 1 from the power, then take derivative of z with respect to x, and that would give you this. Understand? Then I'd have to do plus, and then on the next one, this would be a product rule, somewhere like there, because x is our variable and z depends on x and y, so I would have to do a product rule here. Let me do the product rule real quick. Derivative of this with respect to x would be 6y. And then times the second one, plus the derivative of z with respect to x, which would be partial of z with respect to x, times the first part, 6xy. Do y'all understand that I'm doing product rule on this instead of what we did before? And then I can do partial with respect to x of -1, which is 0. And then we have the other side, partial of a constant is always 0. So here it is. Now, if we go through the mechanics, we could isolate this. We could isolate it, right? We could take these terms to the other side, right? We take those terms to the other side, and then we could divide through. Agreed? Should I do it? I think I should do it because it's not going to look the same. Let me see, plus. So I'm doing this term and this term together, but I'm factoring out the partial of z with respect to x. And then this term and this term I take to the other side. So minus 3x squared minus 6yz. And then I divide through by this. So partial z with respect to x would be negative 3x squared minus 6yz over, let's see, 3z squared plus 6xy. Okay. So what do we have? It's close.
Oh, it should be the same.
Yeah.
You
Is
just
it?
have to distribute the negative through to the top.
Yeah. So that's all it is, I mean, the negative right here. It's not. So do y'all see that we still get the same answers, right? But it's like we have to go through all this work and then solve for this. This formula is a shortcut. That's all it is. All right. So it's not like, I don't want you to feel like we're cheating. We're not cheating. We're just kind of cutting out all this other intermediate work. Any questions? Okay, that would be the partial of z with respect to x. Now, if we want to do the partial of z with respect to y, the only thing that would change in the formula would be the numerator, right? This one up here would change. And that would be the partial of the capital F, which is this side, with respect to y instead. I'm not going to do that one. I'll let you do that yourself. It's very similar work. Okay, y'all all right with that? Any questions? We did that one. All right, so that's it. I mean, that finishes 11.5 chain rule. We basically now know that if we have a variable that depends on other variables, we can create these trees to find these different derivatives. But then also, if our equation cannot be solved for the variable we're interested in, then we can always move everything to one side and use this implicit differentiation and use those formulas. All right. Now we get on to the new topic of today, which is the directional derivative in the gradient vector. So I'll take you back to this, right? I'll take you back to this. When we first started talking about partial derivatives, what we did is, we came and we got to a point on the surface and we said, all right, what we're going to do is we're just going to kind of cut through with the plane by holding x constant or y constant, and then we're just going to look for slopes of tangent lines, right? That's what we were doing. And basically you could look at it as like we were looking in two directions. Do y'all agree this is like just two different directions? So like if I'm looking from the top down, let's see, here's my x-axis, here's my y-axis, the z is coming out towards us, right? If you're standing on top of this surface, you could say that you're kind of pointing in that direction, right? You could also say you're pointing the opposite way, but it's got to be parallel to that plane. So that's one direction we chose, and that direction is actually parallel to the y-axis, isn't it? It's running parallel to the y-axis. And then when we did it the other way, we cut the plane that way, or cut through the surface that way. That means we just decided that we would point in a different direction. We would point like this, which would be parallel to the x-axis, right? But why do we have to point in one of those two directions? Like, there's nothing that says we have to, right? Why not point, I don't know, why not point in that direction like that? And then slice through the surface with a plane that's running parallel to that. And wouldn't you get a different curve? You get a different shaped curve, wouldn't you? And it would then have a different pitch on its line. That's what the directional derivative is all about. It's saying now let's allow ourselves the freedom to point in any direction we want and talk about the slope of the tangent line. So this is actually a more powerful, or more general idea than what we've been doing. All right. So let's get to the notes for this. I always love the directional derivative, right? So we're going to look at a surface right now, and we're going to pick any point on that surface. Okay, so we're going to pick a point in the domain. We're going to go up to the surface, and we're going to be on the surface somewhere. And then once we're at that point, we're going to just pick an arbitrary direction to point, and then we're just going to ask ourselves, what's the slope of the tangent line in that direction? And what we'll see is that the slope of that tangent line will depend on which way we point. So here's a surface. Okay. Can you all see that this black point right here is up on the surface, right? And so now I get to pick a direction to point in. All right. So let me pick a direction. Let me look at this from the top. I forget which is my X and Y axes here. I can't tell. I think this is the X axis. This is the Y axis. So let me turn it from the top here. So it's like you're standing on that black point, right, up on the surface, and then you're going to turn yourself so that when you look down on the ground, like if you could see through the surface, when you look down the ground, you're aiming in that arrow, you're aiming the same direction as that arrow, which is the x-axis, isn't it? In this case, it's the x-axis. And then what we're going to do is we're going to slice through with the plane. So there it is, right? We slice through with the plane in that direction, and then we would have the slope of the tangent line. Right, we'd have the slope of a tangent line at that point. Oops, it got flipped over, but is that all right? Isn't that just the partial with respect to which one? The slope of that line
X.
is the partial with respect to x, because we're pointed down the x-axis, right? And that means we're holding y constant. Now let me move my point. Let me move it the other way. Here we go. So now I've moved my point to a different position. Actually, I went too far down. I'll go up there. Okay. So now I'm in a different position, but again, it's like I'm holding my y constant. So this is nothing different, right? Nothing different so far. Now, instead of pointing in that direction, let's now just start turning in some other direction, anywhere we want. Okay, so I'll turn in that direction right there, and let me flip it back up. And now do you see we have a different curve, right? That's not the same curve we just had. And so the slope of the tangent line should be different. And I can point pretty much in any direction I want. In fact, if I point myself here, right, like that, parallel to the y-axis, that's the partial with respect to y, right? Because it's like holding x constant. Anywhere in between here, right? Anywhere between here, that's pointed down the x-axis, and this is pointed down the y-axis. Anywhere in between is going to be some like combination of the two. It's not one or the other. It's some weird combination of the two. So do y'all understand? That's the goal right now, is to see if we can come up with a formula that will give us the slope of the tangent line if we point in some arbitrary direction. Is that clear?
Yeah.
Okay. Now, here's the formula. And it's called the directional derivative. So if z is a function of x and y, so if you have a surface, then f has what's called a directional derivative in the direction of the unit vector u equals ab. And this is the notation for it, capital D subscripted with the vector u of f of xy, and here's what it is. Okay, we're going to do an example, but I want you to understand something very important here, and that's this direction. So you remember what I said was we have to go here. We have to pick a point on the surface, and then we have to pick a direction. And that direction will always be in the same direction as this red vector here. So we're going to look at that vector, that red thing, that red arrow, as being a vector on the ground. And so whichever way I want to start turning, that vector starts turning, right? And the important thing is for this formula to work, that vector on the ground must be a unit vector. Has to be a unit vector in order for the formula to work. So that's why this is all capitalized. So let's say you have a direction vector, which we are going to call the vector AB. Then the directional derivative, which is the slope of the tangent line we're looking for, is just a times the partial of f with respect to x plus b times the partial of f with respect to y. That's what it is. We're going to do an example. Okay, so let's say we have this function of x and y, x cubed minus 3xy plus 4y squared. Then let's find the directional derivative at the point 1, 2. Right, so what we're doing is we're saying, okay, we're going to, we know that this is three-dimensional, and we're going to go to the point 1 on the x-axis, and we're going to go to the point 2 on the y-axis, some point here on the ground. We're going to go up to figure out where that is on the surface, and that's some point, and the surface is up here somewhere doing something. And what we're doing is we're going to try and find the slope of the tangent line in a specific direction. All right. Now, the direction they give us is not 1, 2. The direction, they say here, the direction vector in the direction of a vector making an angle of pi over 6 with the x-axis. So if we look at the x-axis, that's this. We want a vector, which I'm going to do in black, which is pointed on the xy plane. It's pointed out like this, and it makes an angle here of pi over 6. So if we were to be able to look from the top down here on the ground, we should be pointed in that same direction, parallel to this vector right here. So what we need now, what we need to determine in order to use the formula, the directional derivative, let me write down the formula, of the function is always going to be equal to a times the partial of f with respect to x at some point plus b times the partial derivative of f with respect to y at some point. So that's our given formula. We need to know what a and b are. So the unit vector u has to be a vector a, b, and we don't know what those are yet. So to get those, let's look at this XY plane from the top. We know that we have to be pointed out like this. And we know this has to be pi over 6. So can somebody tell me a vector, what this vector would have to be for what the components of it are? What's A and what's B if this is going to have an angle of pi over 6 and be a unit vector? What does unit vector mean?
It's a length of 1.
Has to have a length of 1. Anyone have any ideas?
Well, it'd have to do with the unit circle.
Yeah, you could just use the things you know about the unit circle, right? This vector would lie on the unit circle. And at pi over 6, what are the coordinates of that point? If it was a point, we would say the point was the point, what, root 3 over 2, 1/2? That would be that as a point. But we can easily turn that into a vector. So why don't we use root 3 over 2, 1/2? Thank you, Fabiola. I saw your chat. I try and pay attention to the chat if I can. All right, so there we go. We know what this is, right? We know what the A and B are. The next thing we need to figure out are what's the partial of f with respect to x and what's the partial of f with respect to y. So let's go ahead and do those. So a partial of f with respect to x. Let's start with that one. So I'm just going to take derivative of this with respect to x, and I'm going to hold all the y's to be constant. So 3x squared minus 3y, and that's it, right? Treating y like a constant, derivative of x is 1, so that becomes minus 3y, derivative of this is 0, derivative of that's just 3x squared. Partial of f with respect to y should just be negative 3x plus 8y. Do I need to cover that? Can I trust that you're all okay with that now? Okay, good. So now we're ready to put it all together. What we would like is to know what is the directional derivative in the direction of the vector u. Okay, so that's what this is saying. Give me the slope of the tangent line if you're pointed in the direction of u of this function, of this surface at the point, and this is where we have to include the point that we're looking at, 1, 2. That should be equal to a, which for us a is root 3 over 2. And then now we need the partial of f with respect to x evaluated at 1, 2, plus now b, which is a half, times the partial of f with respect to y evaluated at 1, 2. And now I just start plugging things in. So root 3 over 2, and then to figure out what the partial of f with respect to x is at 1, 2, I plug 1, 2 into that. And to figure out what the partial of f with respect to y is at 1, 2, I plug it into that. And that should just give me some numbers. So can someone tell me what this first number is? What do we get there? What's the yellow?
-6. Sorry,
Negative.
-3.
Negative 3. Okay, good. And then what about the green?
It's 13.
That's 14.
I think it's 13, right? 16
13.
take away 3. Okay. So we're getting negative 3 root 3 over 2 plus 13 halves. I suppose we could put that all together since they have the same denominator. That would be the exact answer, okay? That would be the exact answer. If we wanted to know what the approximate answer would be, we just get on our calculator. I'm going to do that right here. I'm doing this on my calculator. I hope I'm right here. Approximately, I'm getting 3.9. So let's just kind of remember what this means, okay? Let's say we're standing at the origin okay, on the ground. We're standing at the point 0, 0 on the ground. We aim ourselves pi over 6 from the x-axis, right? Okay. Now we walk out to the point 1, 2. Okay, so we walk out, so we aim pi over 6. We walk out to the point 1, 2, and we still stay aimed in that same direction. We go up to the function, and then we're standing there, and we start taking a step in that direction. As we start to take a step, the slope is going to be 3.9, which means we're going to go up there, right? It means we're headed up. What would we get if we turned around 180 degrees and started walking? We go down, right? We go down, and the slope would still be the same. It'd still be this, but it'd be negative. And the way you could do that is instead of pointing at pi over 6 this way, if you point this direction, right, now your angle is different, right? Your angle would be different. And so your coordinates, your vector, your u would be different. And if you use that different u in here, I promise you, you're going to get the same answer, but it would be negative. All right. Any questions on this? It's pretty nice, right? I mean, this is pretty powerful, actually. Now, when we were talking about the partial with respect to x, and we said you're holding y constant, remember when we did that? I mean, that was last class or class before, said you hold y constant. If you were to do that, and I already showed you the picture of this. Get back to here. This is not the one. So if you go back here to this, and you point out the x-axis right there. Now you're holding y constant, and you move to any point you want. Oh, shit. Hold on, I'm not doing so good here. There. Okay, so you're holding your y constant, right? Can somebody tell me what the red vector is? If we're doing the partial, if we look at this from the perspective from last class and bring it into today, it's the same problem we're doing today, except what's the direction vector?
1, 0.
1, 0. Does everyone see that? Because if you're pointed down the x-axis, your direction vector is the vector 1, 0. And that's a unit vector, isn't it? So look, the formula works, because if this direction vector happens to be the vector 1, 0, then what does this formula turn into? 1, 0, right? It's just the partial of f with respect to x. That's all it is, right? And if you were to point down the y-axis instead, like that, now your direction vector on the ground is the vector 0, 1. And so the formula would work the same way. This would be 0, this would be gone, and then that would be a 1. So it's just a partial of f with respect to y. So that's why I was saying this is a general formula. This allows you to point in any direction you want and talk about the slope. Okay. So any questions? This is like a very important concept in this class, because what we've done is we've established a formula that allows us to analyze how the instantaneous rate of change on a surface at any point in any direction, right? Is that clear? Do I need to explain that in any other fashion to you? This is a big deal. So, no? How difficult do you think this would be then? Let's say I just give you some random surface. There it is. And I go tell you to stand out on that surface, okay? So you're now standing there and you're like looking around, right? How difficult do you think it would be in general for me to then ask you, what direction do you need to point? Okay, so I'm asking you, what direction do you point in so that when you take a step, it is the maximum rate of change that you could possibly get compared to any other direction you would point. Okay, so maybe if you're standing there at this point, maybe if you're pointing this way, you walk and you go up by 2. Slope is 2. Maybe if you turn a little bit, you go up and the slope is 3. Maybe you turn a little bit more, now it's negative slope, right? Maybe you turn it a little bit more, it's a positive slope. So do you think it would be difficult for me to ask you, or would it be difficult for you to answer the question, what direction do you point in to get the maximum slope?
In real life, no. If we were actually standing there,
Yeah, if you're standing there, right, you might be able to tell by looking, right? But I'm saying if I hand you a function, like if I hand you that function right there, and I say, hey, go stand on the point 1, 2. What you just told me is the slope if I aim at pi over 6, right? But what if I ask you, what does this angle need to be so that when you walk, you'll have the biggest slope that you could possibly get compared to all other directions? Does it seem to you like that would be a difficult thing to answer?
yeah.
It is. I mean, it seems like it would be, right? I mean, because you have to compare all possible directions, right? Which would seem like it would be really hard. It turns out it's not hard at all, okay? And that's what the next topic is about, all right? It's about how can we determine that, how can we determine which angle to point to get the maximum rate of change? And I think we have another example before we do that. So let's do this example, then we'll get into the kind of the big deal of today. I mean, this is already a big deal, but there's an even bigger consequence and result of this that's coming. Okay, why don't I give you a minute to try this one? This is very similar to the problem I just gave you. It's just a different function. It's the point 2, 1, and I give you the direction vector. So take about, I don't know, 5 minutes, 6 minutes, and see how far you can go with this, all right? Do y'all want the formula? I'll give you the formula for the directional derivative again. Here it is. That way you have it. All right, there you go. Give you about 5, 6 minutes. And I think I'm going to call on somebody. It's looking like some of you are done. Are there any questions?
I have most of it. I just forgot how to find a unit vector.
Well, at least you remembered you needed to. That's the most common mistake. So how about Jared? Is Jared here? Alberto? Daisy?
Yes, I'm here.
Daisy, are you following?
I'm a little lost.
Excuse me?
I'm a little lost.
Okay. All right, so how about this? How about the partial derivatives? Because in the formulas, you're gonna need the partials, right? Both of them?
Mhm.
Okay, so how do you feel about taking the partial of that with respect to x?
I think I got it.
Okay, what'd you do?
Is it 2x over x squared plus y squared?
Yes, good. Everyone got that? And partial with respect to y is similar to that, but 2y over that. Good, so we'll need both of those, all right? Now, in order to use the formula, Daisy, we need to know what a and b are, right? And a and b are the components of the vector u, but it has to be a unit vector, right? So is this a unit vector? Is its length 1, right? So how could we check that? What is the length of this right now? You just do the square root of the sum of each of the components squared, and you should get root 5. And that's not 1, is it? So it is not a unit vector, right, Daisy?
No.
No, but we can always find a vector pointed in the same direction, right? That is a unit vector by taking this vector, u, and dividing it by its own length. So that means you take each of the components and divide them by the length of this vector, which we already said was square root of 5. Now, I promise you that this vector points in the same direction as u, but does have a length of 1. Does that make sense, Daisy?
Yes.
Okay, so now I can't call this vector u. I'm going to call it v instead, okay? Because I don't want to call it u, right? So for us, what we want is the direction vector in the direction of v of this function at the point 2, 1. So I changed it to v because u was not a unit vector. So I have to change it to v because v is a unit vector. And then that should be equal to the a, which is the negative 1 over root 5. And then I'll leave a space here, plus the b, which is 2 over root 5. And now what we need to do is fill in these spots here. So that means we need to take our partial of f with respect to x, and we need to plug in 2, 1, partial with respect to x, and then the partial of f with respect to y at the point 2, 1 also. And for that, we'll use that formula and that formula. And that's it. Just plug them in. Plug in some numbers here. So let's see what we get. Negative 1 over root 5. Let's see, when we plug in 2 for x, we get 4 on top. And on the bottom, what do we get? 4, 5, we get 5. So 4/5, I believe. Plus 2 over root 5 times, on the other one, we get 2/5. Uh-oh. What do we get here?
0.
We get 0. They have the same denominators, right? So all you do is add up the numerators. You get negative 4 plus 4, you get 0. What does that mean?
No slope.
We have no slope, right? The slope is 0, right? So now you might ask, well, wait a minute, are we at like the top of a hill, right? This is a surface, right? Are we at the top of a hill? Maybe, maybe not. Okay, and that's because this is only talking about the slope of the tangent line in that specific direction. It's not talking about the slope of the line in every direction. So would you all agree, like if we were at, let's say, a sphere, if we were at the North Pole, then do you agree that in every direction the slope would be 0? No matter which way we pointed, we'd have a tangent line that'd be 0. But it is possible that this is more of like a saddle, and that we point in direction and it's 0, but if we turn a little bit, it might go up, and turn the other way, it might go down. So this is not enough. In Cal 1, having a slope of 0 isn't enough either, right? You can think about in Cal 1, if you had a graph that did something like this, of course, here, the slope of the tangent line is 0, so you have like a local maximum. Here, the slope of the tangent line is 0, so you have a local minimum. But here, at this point, you also have a slope of 0, but that's neither a local max nor a local min. So it is still possible that we are not at a highest or lowest point on the graph at this point. We will have a way of finding it, but just not right now. It's not enough information.
Well, at a saddle point though, or a maximum, wouldn't it still be 0 in any direction?
It could be, yes, for a saddle. All I'm saying is that slope of 0 in one direction isn't enough. That's all I'm saying.
Oh, okay.
Yeah. And even if it is, so I think what you're saying is even if it is in every direction, that still may not be enough, right?
Mhm.
Okay, yes.
Oh,
that is
I
true.
see now, because like if it's, let's say, on the side of the parabola and it's going facing in, never mind.
Yeah, you're right. Having a slope of equal to 0 in every direction is still not enough for us to say we're at a top or a bottom. We actually have to do something that has to do with the second derivative, which is going to give us some sort of idea of like a concavity, which is very similar to what we did in Cal 1. Okay, so those first two examples were just to show you. The first example was just say, hey, find the directional derivative, and I'll even tell you the angle. And then from the angle, you are responsible for coming up with the u, right? You had to come up with that. Or I could give you the direction vector, right, that I want you to point in, and you just have to make sure it's a unit vector before you plug it into the formula. All right, we move on. So we want to notice something about this formula. Here's the formula, right? That's the formula for the directional derivative. Could we not write it in a different way? So this is more of like, do you agree or disagree that we could write it this way? Couldn't we just say it's this? It's the vector, it's this vector right here, dotted with the u vector. So let me write this out. This right here, we're saying if we just make up a new vector, we just call a vector partial of f with respect to x, partial of f with respect to y. So I've created this vector, and I'm saying dot it with u, which is just ab. Then if you did this dot product, you would multiply this times this, which is a times that, that's this part, plus b times this, which is this part. Y'all agree with that? It's just, I mean, you might be asking, why would you do that? But I'm just asking you to agree we could, right? We could do that if we wanted to. So that means the directional derivative can be looked at as a dot product. It could be if we wanted to. And that's the way we're going to look at it for right now. The gradient vector, so this is a definition. That vector that we just created, the one that I said, hey, we're just going to call this thing this. We're going to create a vector. That has a special name, okay? Its name is the gradient vector. It's the gradient vector of the function f. And we have a special notation for it. We put this upside down triangle, which is called del f, okay? Del f, or we'll just say gradient of f. is equal to this vector. So we are defining this. From now on, this, by definition, is the vector that is created when you take those two partials and make a vector out of them. And that's called the gradient vector. All right. So do you agree with this now? The directional derivative in the direction of u of the function f of xy, do you agree we could write it this way? Gradient of f dotted with u. Right, that's just now a new notation for it. This directional derivative at some point should just be the gradient of f dotted with that unit vector u. Okay. Now we move on. Or we don't. Sorry. There's that note. Okay. It's coming. It's coming. I'm getting ahead of myself. I'm sorry. So here z is a function of xy. It's e to the xy plus cosine of x plus y. Find the gradient vector. So all we want to do here is find the gradient of f, and that should just be equal to partial of f with respect to x, comma, partial of f with respect to y, and the answer is a vector. So partial of f with respect to x. Let's see if we can do that one quickly. We do the derivatives of these separately. Derivative of e to anything is itself, times chain rule, derivative of the exponent with respect to x, which means we treat y like a constant, so our answer there should be y. Plus, now the derivative of cosine, oops, maybe I should make that minus then. Minus sine of x plus y, but then the chain rule says now times the derivative of the inside with respect to x, which is just 1. So I actually don't need that dot. That's the partial of f with respect to x. Now I do partial with respect to y, which is going to give us something very similar, except we're going to have e to the xy times x instead of times y. And then we'll have minus sine of x plus y. Chain rule, derivative of the inside with respect to y is still 1, so that's it. That's our gradient vector. Everybody agree? That's del f, that's gradient of f. This is just an exercise. Understanding the terminology. Can I move on? All right, so now let's extend this concept out into higher dimensional space. So what if instead of having z as a function of x and y, what if we have some function that is a function of x, y, and z? Now this is where we have trouble because we can't visualize this function because it requires 4 dimensions, but we can still define everything the same way. We can say, all right, it has a directional derivative in the direction of the unit vector. This time it's a 3-dimensional unit vector, ABC, and it will be defined as a times the partial of f with respect to x plus b times the partial of f with respect to y plus c times the partial of f with respect to z. So it's everything we just did. We're just adding this new piece out here, and our directional, our direction vector is actually 3-dimensional. So this is where it's impossible for me to get you to understand what's going on visually, because I can't tell you to go stand somewhere and point in a direction, because there is no surface to look at. The surface is in 4-dimensional space. Everything else is the same though. We have the gradient of f is just a vector that we create that is now a 3-dimensional vector made up of the 3 partial derivatives. All right, let's try this. I think I'll copy this over. All right, so first part A, we want to find the gradient vector. So we recognize that this is a function of 3 variables. So our gradient of this should be a 3-dimensional vector made up of the 3 partial derivatives. All right, so let's do this. Partial of f with respect to x. Anybody, can anybody tell me what the partial of f with respect to x is?
One over y plus z.
Yeah, I
Yeah.
would look at this as, that's the same, this is the same as this. And since y and z are being held constant, this is just a big constant in front of x. So derivative of that with respect to x should just be the constant in front, 1 over y plus z. Good. Now the partial with respect to y. Now that's a little different, right? That's a little different. Because I think in that case, you would have to almost treat it like this. And then when you take the derivative of this, you'd have to maybe do a quotient rule. Now you could bring the y plus z up as a y plus z to the -1. It's kind of up to you, but I'm going to do it like a quotient rule. So the derivative of this with respect to y would be equal to the derivative of the top with respect to y, which is 0, times the bottom, minus the derivative of the bottom with respect to y, which would be 1, times the top, which is x, and then all over the bottom squared. Y'all following me? Any questions? Negative x over y plus z squared. The last one, partial with respect to z of this same thing. I have to do the same, pretty much the same thing I just did. Is the derivative of the top with respect to z, which is 0, times the bottom, minus the derivative of the bottom with respect to z, which is 1, times the top, all over the bottom squared. So you get the same thing, negative x over y plus z squared. That's your gradient vector. You ready for part B? We want the directional derivative at the point 411. So 411 is our x, our y, our z, and we want it in the direction of the vector 1, 2, 3. So is 1, 2, 3 a unit vector? It's not, right? The length of that vector, if we take the length of that vector, we get square root of, let's see, 1 squared is 1, 2 squared is 4, 3 squared is 9. So this is root 14. That's not a unit vector. So to make it a unit vector, we're going to take this vector and we're going to divide it by its own length. So 1 over root 14, 2 over root 14, 3 over root 14. And let's call that vector v. So that when we apply the formula, the direction vector in the direction of v of this function at the point 411 should be equal to the first component of the direction vector times the partial of f with respect to x at 411 plus the second part of the second component of the direction vector times the partial of f with respect to y at the point 411 plus the third component of the direction vector times the partial of f with respect to z at the point 411. And then from here, what we do is plug in and get the answers. Like this right here is that. We have to plug 411 into that, and 411 into that, and then 411 into that, and that'll give us those three numbers. We should be there at that point. So 1 over root 14. Let's see, partial of f with respect to x, we plug in 1, see, so that should be 1/2 plus 2 over root 14. And then we plug in 4. On top, we get -4. And on the bottom, we get 2 squared, I believe. 1 plus 1 is 2 squared is 4. So we get -1 there. And then plus 3 over root 14 And we should also get -1 here. So I get 1/2√14. That's the first piece. And then these two I can put together because they both have √14 in the denominator and they're both negative. So I think mine is 5/√14. Right? -2/√14, -3/√14. Add those up, you get this. And then we get a common denominator, multiply 2 here and 2 here. And then do 1 take away 2 times 5 is 10. So you get -9/2√14. There you go. Now, when we had a function of 2 variables, the direction derivative makes a little sense. Because you walk out to a point, you go up to the surface, you aim in some direction, you take a step, and it's telling you if you're going up or down, right? That's what it is. If it's a function of 2 variables. Here I said it's hard to understand what's going on, but I can give you an example. I'll give you an example that would make a little sense, okay? So let's say that we have some object, okay? It's 3-dimensional. Okay, so this is like some, you know what? Let me do it this way. Some three-dimensional solid. Okay. Or actually, let's not make it solid. Let's just say it's a surface. All right. And this, if you go to some point on this surface, right? You could be on the side, you could be underneath, you could be on the back side, doesn't matter. You just go to some point on the surface. Then we have a function, f of x, y, z. And let me just tell you that that function gives you the temperature at that point on the surface. Okay, so when you're standing right here, you have a certain temperature, right? If you go to another point on the surface, maybe here, you have a different temperature. Make sense? So the directional derivative in some direction v of this function, what it would mean is, let's just say we take that blue point right there, okay? What we do is we'd be on that blue point, and then what we'd be doing is we'd be saying point in some direction. So you have a directional vector v that points in some direction in 3-dimensional space. So point here, let's say, that's v. And now start moving in that direction. As I move in that direction, the directional derivative is going to give me the instantaneous rate of change in temperature. So it's telling me as I move in that direction, how rapidly is the temperature changing? So it might be hotter in that direction, it might be colder. If it's a positive number, it means temperature is going up. If it's a negative number, the temperature is going down. Does that make sense? Okay, so that's how you can kind of understand what's happening when you have a function of 3 variables like this. Now, if you go to a function of 4 variables, now that's where we have to give up. I think at that point you have to give up, because now I have to ask you to think about a point that's in 4-dimensional space. And that would be hard for you to understand, right? For all of us to understand. All right, any questions? All right, so here's the big other part of this section. Finding or maximizing the directional derivative. This was the question I asked you earlier. I said, if I tell you to go stand on some surface and you tell me which way to point so that it will give you the maximum rate of change, that's called maximizing the directional derivative. So remember that when we were studying dot products, that there was a formula for dot products that went like this. U dot v is equal to the magnitude of u times the magnitude of v times cosine of the angle between the 2 vectors. Remember that formula? But we just, for some strange reason a moment ago, I said, hey, the directional derivative, we could, if we want, look at it as a dot product. And the reason I did this is because if we look at it as a dot product, then using that formula, this just becomes the magnitude of the gradient vector times the magnitude of u times cosine of theta, using that formula, right? Right? But what can you tell me about the magnitude of u?
It's 1.
It's 1 because it was a unit vector, right? This was a unit vector. So that means that the length is 1, right? So if I replace that with the 1, then now what we're saying is that this becomes this, right? The directional derivative, right? The directional derivative is simply equal to the magnitude of the gradient times cosine, excuse me, cosine of the angle between the gradient vector and the direction you're pointing. Let me say that again. The magnitude, or sorry, the directional derivative is simply equal to the magnitude of the gradient vector times cosine of the angle between the gradient vector and the direction you're pointing, right? But if you want this to be as big as possible, right, the largest this could ever be is when this right here is 1. And that only happens if that angle is 0. And so that means that the angle that you need to point in has to be exactly the same as the, well, sorry, the direction you need to point in, right? The u, that direction, needs to be exactly the same as the direction of the gradient vector. And that means that the gradient vector tells us everything we need to know. The gradient vector, right? The direction of the gradient vector is the direction of maximum rate of change. Okay, so let me see here. So I'm saying, you know, u must be 0. The angle between the two has to be 0 in order to attain the largest directional derivative. And that takes us to this ultimate result. The maximum value of the directional derivative is simply the magnitude of the gradient vector, and it occurs when we point in the direction of the gradient vector. Now, for me, this has always been just mind-blowing, because all you need to know about which way to point to go up the highest or go up the fastest is all you need to be able to do is calculate partial derivatives. If you can just calculate those two partial derivatives, you're done. You're done. So let's see it in action. Okay, let's say we have this surface. It's a function of two variables, sine of x minus y plus cosine x. First, find the direction as an angle of the maximum rate of change at 0, 0. And then tell me what the maximum rate of change is. All right, that's what we're gonna do. So first thing we're gonna do is we're gonna copy this over. And I want you all to appreciate what's going on here. We're in three-dimensional space. We have a surface. Whatever it's doing, it's doing. We're going to the point 0, 0 on the ground, and we're going up to somewhere on the surface, right? Boom, there it is. And what we're about to find is we're about to determine what direction we need to point in on the ground. What direction do we need to point in order to get the maximum rate of change up here on the surface? And once we find out what that angle is, or you know what that direction is, then we're going to actually ask for that slope, and that's the maximum rate of change, right? So to answer part A, what we need to do is figure out what the directional derivative is at 0, 0. So here, all we want is the directional derivative of f at the point 0, 0. Okay, well, sorry, the gradient vector. I meant to say gradient vector, not directional derivative. The gradient vector itself is just this vector, which we should be able to crank those partials out pretty quickly. Let's see, derivative of this first part is going to be cosine of x minus y times the derivative of the first, or the inside with respect to x, which is 1, plus the derivative cosine of x, which was negative sine x. Okay, that is the partial of f with respect to x. Now we do the partial of f with respect to y. So here we're going to get, now again, derivative of sine of something is cosine. What about chain rule? What does chain rule spit out here? Derivative of the inside with respect to y?
It's a negative one.
Negative 1. Okay. And then we do plus the derivative cosine of x with respect to y, which is 0. So that's it. That's our gradient vector. Okay, that's our gradient vector. Now all we need to do is take that gradient vector and plug in 0 for x and 0 for y. And so when we plug in 0 for x and y, we get cosine of 0 minus sine of 0. And then we get cosine of 0 times negative 1. So cosine of 0 is 1, sine of 0 is 0. So I get 1 here and I get negative 1 there. This vector is pointing in the direction that I need to point in order to get the maximum rate of change. So if we look at this picture here, looking from the top down, here's x, here's y. We need to be pointing in the direction of this vector, 1, negative 1, which means to the right 1, down 1. Here's the direction we need to be pointed in. Now, part A asked for that direction as an angle. So what is that as an angle? Relative to the x-axis. Negative 45. So the answer to part A is negative 45 degrees. If you want, you could say, 335. That would be okay. Now, what is the maximum rate of change? That's the angle we need. That's the direction we need to point. But what would our maximum rate of change be? Part B. All it is what?
Was it the absolute value of the gradient vector?
That's right. It's just the absolute value or the magnitude of the gradient vector at that point 0, 0. So that's just going to be the magnitude of this vector 1, negative 1, which is the square root of 2.
To find the angle, we would use tangent or inverse tangent.
You could have used inverse tangent, yes. Yeah, because sometimes these angles aren't going to be easy to find like this one. You could have done arctangent of theta equals negative 1 over 1. I'm sorry, no, arctangent. Arctangent of negative 1 over 1, and that would have given you negative 45 degrees. As long as your calculator was in degree mode, it would give you that. All right. I don't know. I mean, to me, I've been doing this for years. I've been teaching this for years, but to me, this has always just blown my mind because we have some arbitrary function here. And I know that if I go to any point, doesn't even have to be 0, 0, right? It can be any point I want here, anything you want. You want to go to the 0.25? Sure. Then if you go there and you walk and you're up on the surface, I can tell you after just a couple of quick calculations, I'll be able to tell you what angle or what direction to point in so that if you walk in that direction, you are going to be going up the steepest. Another way to kind of understand this question is that if you were to take a ball, right? If I were to take a ball and place it at this point right here, right? This direction, negative 45 degrees, would tell me which way that ball would be going uphill the steepest, right? But if I point in the opposite direction, right? If I were to instead of pointing here at negative 45 degrees, if I were to point in the opposite direction, then that would be the steepest descent, wouldn't it? And that would be the direction the ball is going to go if I let it go. Right? So for any surface that we know the function of, right? We actually know the equation of the surface. We can go to any point on the surface, put a ball there, and I will be able to tell you which direction it's going to go, exactly and precisely. It would always be pointed in the opposite direction of the gradient vector. And the rate of change would just be the magnitude of the gradient vector. Pretty awesome, I think. Have you all, well, I know you've seen these before. Oops, I misspelled contour. Y'all seen these before? Contour maps? So contour map is a map of like a hill, right? And the lines along the contour map show you the path along this hill. Well, here's a good picture. The contour map shows you the path along a hill where the elevation is unchanged, right? Where it's unchanged. So the way you can do this is, that's basically saying what direction, so you're standing at a point, right? And there you're saying, what direction would I point in so that I don't go uphill or downhill, right? I want to stay flat the whole time, which means it's the same question we just asked, but instead of asking for the maximum, we're trying to figure out where is the magnitude of the gradient vector 0, right? Basically, what direction do I need to point in so that I get 0 incline or decline? And if I keep doing that at every point, I create the contour map. So this is related to contour maps. Okay. Let's do one more thing, and then I think I'm going to have you do that problem, but let me get to the last thing here today, which is tangent planes to surfaces. So we already talked about tangent planes to surfaces back in a previous section, right? I think it was 11.4. We talked about tangent planes, and I gave you a formula. Here was the formula. It said that if z is a function of 2 variables, then you can always find the equation of the tangent plane by using this formula. And I told you that the first part, the number in front of the x minus x naught, that's just the partial of f with respect to x. This is partial of f with respect to y. And I told you this would always be -1. Remember me saying that? I said, don't worry about that later. I'll show you where that's coming from. Well, now it's time to show you where that's coming from. So given an equation of 3 variables, we can always write, or if we can rewrite it as capital F of x, y, z equals a constant, then the equation of the tangent plane to this surface at some point is this. Now I know that looks ugly, but this all here is like a in front of x minus x naught, plus all of this here is like the b times y minus y naught, and then all of this right here is like the c in front of z minus z naught. And we know that right there that I just did is the basic general equation of a plane, right? So the a part comes from taking the partial of f with respect to x. The y part is partial of f with respect to y. And the z part, this c part right here, is the partial of f with respect to z. All right? And so these partials make up the normal vector of the plane. Let's do an example. You'll see it in action. So here we have an ellipsoid, right? It's an equation containing 3 variables. And what we're going to try and do is find the equation of the tangent plane at a specific point. So in order to do this, I need to be able to take 3 partials, and we have to be able to look at this as being some capital F of x, y, z equals a constant, which I think we have, right? That's what we have here. As long as we have this, then we can crank it out. So let's get the partial of f with respect to x. This will just be 2/9 x. I'm going to trust that you get this. Partial of f with respect to y would just be 2y. Partial of f with respect to z would just be 2/25z. Y'all agree with that? This is our x naught. This is our y naught. This is our z naught. And so now I'm ready to go into the formula. So I need to take this and figure out what this is at that point, -3, 4, 5. But it only has x in it. So I just need to plug -3 in there. So we get -6/9, which is -2/3. We do this one. I need the partial of f with respect to y at that point, -3, 4, 5. But it only has a y in it, so I just plug in 4 here. I get 8. And then last one, partial of f with respect to z, but at the point -3, 4, 5. But it only has z in it, so I plug in 5 into this, and I get 2/5. So this vector, the normal vector of this plane that's tangent to the surface will be -2/3, 8, 2/5. And once I have the normal vector in the point, I can put it all together into the equation. So the equation of the plane, tangent plane. I know I'm working. I had a double negative. That's why that is, yeah, x, I had a minus 3, so that's why it's +3. And then 2/5, and then z minus z naught, which is 5, equals 0. There it is. There's the equation of the tangent plane. This okay? All right, so I'm going to go back to that previous class where we had this formula right here. And now I'm going to explain to you why this is -1. I think it'll be pretty easy for you to see, hopefully. If z is a function of x and y, then I could always move the z to the other side. So I can make this 0 equals f of x, y minus z. And then treat this whole thing as my capital F of x, y, z, and use the formula that we just did. And if we do that, then when I do my capital F partial with respect to x, it will just be, since this has z in it and no x's, it'll just be the partial of this with respect to x. When I do the partial of f with respect to y, since this just has z, it would be the partial of this with respect to y. And then now when I do the partial of this thing with respect to z, what would I get? This doesn't have z in it, right? So derivative of that would be 0. This is the only thing that has z in it, but it's exactly z minus z. So derivative of that's -1. And so you can see, hopefully you can see, that this -1 is always the thing in front of that, right? This is the thing in front of that, and this is the thing in front of that. So that's where the -1 came from. It came from the idea that later on, when we get the more general formula, if you can solve this for z, then when you move everything to one side, that partial derivative will always be -1. All right. So I think we're done with this. Let me make sure. Yeah. Okay, this was just to show you that what we just did. We had an ellipsoid. The point we were talking about is over here on this back side, and then we actually found the equation of that plane that is tangent to the ellipsoid. Okay, that's what we just did. Oops. All right, we've got about 8 minutes. What do you say you just try that one? I'll put it on a separate sheet and then I'll bring the other problem in there in case you finish that one and want to keep working. But we're pretty much done for the day in terms of this material. So we'll be ready to move on to the next section next time. All right, so there's 2 problems. We only have about 7 minutes. Just work what you can. I'm going to just kind of mute and take my video off. And what I'll do is I will work it out also on the side. And that way you can see if you're getting the same thing. The first problem is a function of 2 variables. And the second one is a function of 3. So, you know, the formulas are pretty much the same, but you just have to pay attention to what's going on here. I'm starting to wrap things up here. Okay, I'll just talk through this. You're free to go if you want. So on the first one, we want the direction is an angle of the maximum rate of change. So that means we need the direction of the gradient vector. So we take the gradient, which means we take the partials, then we plug in the point we're talking about, 1, 2, and we get this vector 1, -2. Then we just need to figure out where that is. And so I like to draw a picture, 1, -2, that puts it in the fourth quadrant. And when you do arctangent of this, you get -63.4 degrees, which makes sense, like it matches. You have to be careful with that, because if we had gotten a vector, let's say our vector here would have been -1, say -1, 2, then it would have been here -1 and then 2. It would have been this, but our answer on our calculator still would have been -63 degrees. And that's not the same angle, because your arctangent function has a domain restriction. It only looks in the first and fourth quadrants. So it thinks you're over here in the fourth when you're not, you're actually in the second. So you would have to realize that this angle here, -63.4, is the same as this angle here. So the angle you'd be looking at is 180 minus 63.4. So just be careful with that. Part B, just find the maximum rate of change. So you just take the magnitude of the gradient vector, which is this. Now on this next one, find the directional derivative at this point in this direction. So this is where you have to first make this a unit vector, which I did here. And then you need to find the gradient vector, which I already did over here. And then you dot the two and then plug in your points, so you get an answer. And then this part, you take the gradient vector, you go to the point 1, 3, 0, plug in, and you get this vector. And then you find its magnitude, which is 3. And one thing you should note is that this answer should always be bigger than that answer, because the magnitude of the gradient vector gives you the maximum rate of change. And so if you point in any other direction, that number should be smaller. Like this number should never be bigger than this one. It should be the biggest you ever get. All right, any questions before we wrap it up? I saw some stuff here on the chat. If anyone needs to talk to me, I'll be in my office tomorrow during office hours. If anyone wants to talk to me about the midterm. Okay. All right, y'all are free to go. I'll hang
Awesome.
out here
Thank
for a
you.
minute. If you need me, I'll hang out here for a minute.
Thank you.
Excuse me, Professor.
Yes, sir.
One sec. I just have to click a button on my computer. If I can click it, there we go. Yeah, I'm just, I follow along in class with everything that's going on, and I understand the material, but I don't think I understand it to the point that is expected of me for these exams.
Yeah.
So I was wondering if there's like resources that the Alamo community gives out during these times for free tutoring and whatnot.
Well, there is free tutoring. Now, the limitation is that you're going to be asking to get help in Cal 3, which is really kind of the peak of what we offer in the school, right? And then, so the tutors we have are going to be limited in what they know, right? So it's not like a university where you have people who've been through all the calculus sequence. Most tutors at a university already have their like undergraduate degree and they're working on their master's or PhD. So they can tutor a lot better in Cal 3 than someone like at Alamo colleges, where most of the tutors have taken Cal 3 maybe, or taken Cal 2. So I'm not quite sure who I could point you to within the Alamo colleges for tutoring. Which is why I always told you all that you're free to reach out to me. So are you available during office hours, or is that just doesn't work out for you?
So what time specifically are your office hours again?
Okay, they are Monday and Wednesday.
Then yes.
Okay, Monday and Wednesday, they are between 11 and 1, so 2 hours before our class begins. And then on Tuesday, Thursday, they are from 10 to 1. And then I'm available by appointment. You can always work something out with me if you want to meet at a different time. We just have to arrange that.
Okay, how busy are your office hours 2 hours before class?
Before class, I don't have people come consistently. I have like 1 or 2 students that come consistently. But whenever, we get closer to exams and stuff, I usually get more people in there. I can't tell you how many people would be there on, are you saying on Wednesday?
Yeah, like Monday and Wednesday, because I work a lot on Tuesdays and Thursdays, but just Monday and Wednesday. Actually, Wednesdays, do I work?
You would probably have a lot of, I would be available quite a bit, I would think, unless all of a sudden I start having a bunch of students showing up. I mean, I never really have more than 2 people in there at one time. And yeah, I mean, you could just try it, see how it is.
Yeah, I'm just like one of those people, like the numbers all make sense to me, but when I have to start digesting a problem, it takes me too long, and then I'm like, which, strategy technique do I want to use? Like, what was it? Finding, I think it was like on the midterm, one of the questions was finding the maximum point on a quadratic surface, and my brain just kind of fell apart. I was like, I know I have to take the second derivative at some point in here. Let's see, I think it was actually just like question 1 or 2. I have this actually open somewhere on my computer. God forbid I have less than 30 tabs.
Yeah, so I mean, on these problems, what I'm really asking is beyond what, well, it's beyond what the textbook is asking, right? It's asking for you to make connections to stuff that even goes back to like Cal 1, Cal 2, pre-Cal. I mean, this is, to me, Cal 3 is like the capstone course of calculus, right? This is the end of the calculus sequence, right? So I'm trying to like stir up all this old math in you to get you to like think about things from a holistic perspective, as opposed to just, like the problems we do in lecture. I mean, these are very mechanical problems once you understand the process, but you need that mechanics to be able to answer harder questions, which is what I'm trying to give you on this take home, or harder questions where you can use what you've learned along with things that learned in this class, along with things that you've learned prior to this class, to answer some rather complicated sounding questions, even though they may not be as complicated as you might be wanting to make them. So it's problem solving, really, is what I'm trying to get you to do here.
I totally understand that. It's just, picking out which mechanical skills I need to use. Like question 1, for example, is a perfect example.
Okay.
I could probably find spheres with a tangent to the YZ plane with a radius 9, but then all of a sudden the center has to have 2 planes passing through it in a form for a plane I've never actually even seen before. So,
okay, so I'll help you with this one just to show you that you can overcomplicate things. All right, so all spheres have an equation: x minus h squared plus y minus k squared plus z minus l squared equals r squared, right?
okay.
Okay, now the only thing that you need to determine is HKL, right? Because that's the center of your sphere, right? That's the center. And you need to know what R is because that's your radius. But I've already told you what the radius is, right?
9.
9. Okay, so you know that this is 81. All right. Now, the fact that you have to be the center, right? This point HKL must pass through these two planes means that, let's see, what does it mean? Well, whatever H is, what can you tell me? Whatever H is, say you know what H is, right? What would K have to be? Let's say you know H. Well, K is the Y coordinate, right?
Mm-hmm.
Is there anything you can tell me if you live on this plane and you live on this plane, what's the relationship? The X has to, the X, whatever the X is on this plane, if you multiply it times 5, you get the Z, right?
Yeah, I could set them equal to each other, right?
Yeah, you could do that. You could do that. Let's see, if you set them, you have 5X must equal 15Y, right? So X must equal
3Y.
3Y, okay. But remember, H is your X coordinate, right?
Yeah,
So if you know what H is, can you tell me what the Y coordinate K would have to be?
3 times H.
Other way around. The Y would have to be a third of, because you just solve this for Y, right? Solve this for Y,
Oh, okay. Yeah,
right? So the Y coordinate would have to be a third of X. So if you know what H is, do you agree that the Y coordinate would have to be H over 3?
okay.
Okay. Now, if you know what H is, do you know what the Z would have to be?
Z would have to be 5 times H.
Okay, 5H. All right. There you go. Okay.
And then I guess with.
So now all you need to know is what H is, right?
Mm-hmm.
Okay, so you've got a sphere that lives in three-dimensional space and is tangent to the YZ plane, right? Tangent to the YZ plane. So if this is X, this is Y, this is Z, right? If you're tangent to this back wall, then that hits your YZ plane, right? Like a radius here hits your YZ plane.
Yeah,
Can you tell me what this would have to be then? From here to here?
the distance is 9.
9, right? But
Yeah.
isn't here, let me do it from the side. What if we had a ball that touched a plane, right? Like this? Wouldn't
Okay.
this distance here 9, wouldn't it also be one of the coordinates of the plane? I mean, coordinates of, wouldn't it be one of these coordinates?
Oh, yeah, I guess it would be then.
Which one?
It would, well, let's see, that would have to be our X.
Yeah. So you know that this is actually 9, right? And that would make that next one be 3. And that would make our next one be 45. And now you have the center.
And then I guess I'd have to,
No, you're done.
I thought it was, I thought that /S meant find.
Okay,
all
so
the spheres.
maybe you would have to convince yourself that maybe there is another plane, right? But maybe there's not. See, because these two planes, right? These two planes, the center must go through those two planes. So even though there could be a sphere on the other side like this, right? Where that's 9 also, here's your plane.
Yeah,
Would this point lie on both of those planes?
I don't know.
Yeah, so you try it. What if this was, think about this. If you were on the other side, what would your X coordinate have to be if you were on the other side of the YZ plane?
-9.
-9. So if that's -9, then the other one would be -3 and the other one would be -45, right?
Yes.
And would all these relationships still hold? So is Z this times 5? Yeah, right? Is Z this times 15? Sure.
So it also does hold for the other side then, right? For
In
when
this,
X
in
is
this
big.
case, it does, yeah.
How would, this is where I get like, worried. did I find all the spheres? Am I missing? Is there some general rule of thumb that would help me figure them all out that I should know that I don't?
Well, so because these relationships have to hold, right? Those have to hold because that's coming from these, right? Then if you can nail down just one of these, right? If you can just nail down what H is, then you're done. But to be tangent to the plane YZ means that you have to be one of these two pictures. You can't, there's no other way to touch the YZ plane and have your X coordinate not be 9 or -9.
Well, what if we were still touching the the YZ plane just on the other side of the X,
Touching the YZ plane on the other side.
So
of the
like if we were to extend Y into the negative direction, we could then essentially be on the, I don't know which octet it would be.
Oh, I see what you're saying. Well, remember when we said originally that this, you see in blue here, that had to be 9, that moved our sphere so it just touched the YZ plane, right?
Yes.
Okay, and it did not tell us left or right where we were, did it?
Yep.
It just forced us out. The thing that determined the left and right and the up and down of this sphere was these two coordinates. So if I'm being forced to have my X come off +9, that forces my Y to be 3, and it forces my Z to be 45 in order to go through those two planes. I cannot slide this. I can't move this over here to the left into the negative Ys, because what happens if I make this Y coordinate negative?
Well, screw up
then
the
the X coordinate
relationship.
has to be negative too, right?
Yeah.
See, but that's this case.
Okay. I
So
guess that makes more sense to me.
yeah, it's because the X, Y, and Z are all interconnected that there's not an infinite number of spheres. Let me see here. Here, I think I might be able to do it. I've got to go soon, but might be able to do it on a new page.
It was what's it called? Passing through the center of the planes is what really started to mess with me, because I could always at least sketch a picture normally of where my planes are,
Yeah.
but those planes were just.
So if I had two planes, right? The only thing that they have in common would be a line of intersection, right? I mean, unless they're the same planes. If they're the same planes, then every point is a point of intersection, right?
But we know they're not the same plane.
But we know they're not the same, right? And they're not parallel to one another because they don't have the same normal vectors. Do you agree with that?
Yes.
So that means that their intersection is a line. Do you agree?
Yeah.
Okay, so get rid of all this then. The center of your sphere has to lie on a line then, right? But then you've got the whole YZ plane here somewhere, right? Here's your YZ plane. And you're going to have a sphere that's on one side that has that line on it, and on the other side, somewhere else, it's going to have the center. Does that make sense?
Okay.
So if I draw it another way, here's that plane looking at it from the side, and then you've got the line that went through somewhere. You've got one sphere that's like this, and then another sphere over here that's like that. But you can't move these around. You can't slide these spheres around because their centers have to be on a line.
Okay. Yeah, I'm more comfortable with that. I was overlooking the fact that it's limited to that line segment.
Yeah. So every single one of these problems is supposed to kind of get you to be thinking a little bit different than you normally would think. And I want to be able to talk through these things with you. That's why I've told you can reach out to help, for help. I encourage you. I've been telling y'all, please, I never intend these exams to be something you do completely with no help. It's because this dialogue is important to getting you to start thinking about things a certain way. Now, I don't know what your availability is in the evenings, but I'm around. If you're available in the evenings, I'm happy to try and meet up with you, especially if you're really kind of like not, if you haven't done a lot of this and it's due in like less than 48 hours, you might want to try and meet with me either later this evening or tomorrow evening or something.
Yeah, I've done about 3 questions.
Yeah.
So
Okay.
I
Well,
could,
if you text me later, I've got some commitments probably until about 7 p.m. But if you text me after 7, if I'm available and near my computer, I'd be happy to jump on Zoom and we can kind of just like talk through some of this stuff. I mean, the first one, I walked you through the whole thing. The next, I would give you hints to try and get you going. But we can refer and we can look at all of it,
okay, I would really appreciate that. Yeah, I don't want you to like give me the answers or like show me the whole thing, but a little bit of hand holding, a little bit of help would be very much appreciated.
Yeah. no,
Because I really know I can do all of these. I just, I totally understand that you're trying to come at this from a different angle, critical deduction skills and critical, what's the dang terminology I'm looking for? Critical problem solving.
Yeah, just critical thinking in
Oh,
general.
that's the one.
Yeah. Okay,
Um,
well, text me later and I'll try and meet up with you if I can.
I appreciate it.
Okay, all right,
All right.
Daniel. All right,
Have a good
talk to
one,
you later.
Professor. Thank you.